This chapter we're going to be going over another technique for taking the derivative, and it is called the chain rule. So what we're going to be doing is actually showing that we actually know how to do this already, and that is because we've already learned how to do the general power rule, and the general power rule is a specific case of the chain rule. So we actually pretty much know how to do this already. So before we get there, let's actually go over and review what a composite function is, or composition of functions. Composition of functions is going to be a way that we can combine functions, and what this is having one function be the input to another function, and the resulting function is called a composite function. The way that we denote them is like this, and we read it as f of g of x. It could also be denoted with this little circle. They mean the same exact thing. So in this case, that means we plug in g of x into all of the x's in f of x. Okay, let's see an example here. Let's say we have f of x is x minus 1 over x plus 1, and g of x is x cubed. We want to know what is f of g of x. So f of g of x is going to be plugging in g of x into f of x. So instead of x minus 1, it's g of x minus 1 over x plus 1 becomes g of x plus 1. So everywhere there's an x, we replace it with a g of x. And now let's actually plug in g of x. We know that g of x is x cubed. So that's x cubed minus 1 over x cubed plus 1. Okay, so this was a pretty simple case. That's actually as far as we can go. So that is our answer, the composite function f of g of x. So we can actually go the opposite way as well, and that's called decomposing composite functions. So let's take a look at this first one. We have h of x is x to the 5th plus 9x plus 3 to the 8th. We want to write this as a composite of simpler functions. So that means we're going to have f of x and g of x be smaller functions, and we're going to rewrite h of x as f of g of x. That means, the way that I've said it, that means f of x is the outer function and g of x is the inner function. So it's pretty simple once you get a hang of it. This function has this inside x to the 5th plus 9x plus 3. The way that we can do it is we can just always let g of x be whatever is on the inside. Technically, there's going to be multiple ways to do these, but you can always just let g of x be whatever is on the inside, and it should always work. And then we think, okay, well, what is the outside function? The outside function is the inside function being raised to the 8th power. So all we have to do is say that's going to be x to the 8th power. So x is just saying something to the 8th power. So what that means is that h of x equals f of g of x. And that is because f of g of x, you start with f of x and you plug a g in. That's going to be g of x to the 8th power, which gives us the desired function, which is x to the 5th plus 9x plus 3 to the 8th power. Okay, so you just let g of x equal whatever the inside is, and f of x is the outside function, which is typically an exponent in this case, and it's as simple as that. Take a look at another one. We have k of x is the square root of 4x squared plus 1. So let's go ahead and let f of x be the outside function, g of x will be the inner function. So the inside function here is just 4x squared plus 1. It's whatever is inside the inner function here, in this case inside the square root. And now the outside function is obviously the square root, and you just make it nice and easy, and it's just the square root of x, just like before. So now we know that k of x is going to equal f of g of x, because that's how we set it up. and that is because f of g of x is going to be the square root of g of x, which is the square root of 4x squared plus 1, which is exactly what we wanted. Okay, so this brings us to the idea of the chain rule. What the chain rule does is it actually helps us find the derivative of composite functions. So that means we're going to have a function, h of x, where it is a composite function, f of g of x. And if we take the derivative of it, what we do is we take the derivative of the outside, leave the inside alone, times the derivative of the inside. So f prime of g of x times g prime of x. And once again, we already know how to do this because it's essentially the general power rule. And we will come across one question I think I put on here where if we have this other Leibniz notation using the differentials dx, dy, if we have y equals f of u and u equals g of x, then we could take the derivative of f of g of x, take the derivative of the composite function, and another way to write it would say, okay, that would be dy dx. But in this case, what you would actually have to do is you take the derivative of y with respect to u, and then multiply that by the derivative of u with respect to x. And you can kind of see here that the du's cancel, and that's why you get dy over dx as your answer. So that probably looks a little confusing, but we'll come back to that. I think it's the last example. Okay, and just like I've been reading it off is right here. We can read off the derivative using as the chain rule as the derivative of the outside, leave the inside alone, times the derivative of the inside. So let's do a couple examples. Let's do the derivative of x squared plus 3x minus 2 to the 100th power. So this derivative, this is just the general power rule, right? You bring down the 100. You leave the inside alone. Oops, you leave the inside alone, so x squared plus 3x minus 2. Subtract 1 from the exponent, times the derivative of the inside. The derivative of the inside is going to be 2x plus 3. So all we have to do is pretty much just clean it up. Maybe write this as 100 times 2x plus 3 times x squared plus 3x minus 2 to the 99th power, and that is it. So we could have already did this, but now we know it's called the chain rule. Let's just do a couple more examples. Let's find dy dx, find the derivative, where y equals 1 over the cube root of x squared plus 1. So we have to know that we can rewrite this as 1 over x squared plus 1 to the 1/3 power, which means we can rewrite this as x squared plus 1 to the negative 1/3. So we have to do that because it has to be in the numerator in order to be able to do this. Notice that I did not bother using quotient rule here because it would have just been messier. Technically, you could use quotient rule and you should get the same answer. Let's go ahead and find the derivative. So obviously we're basing it off of this version right here. So you bring down the exponent. So derivative of the outside, leave the inside alone. Negative 1/3 minus 1 is negative 4/3 times the derivative of the inside. The derivative of x squared plus 1 is just 2x. And we can simplify it. And we can write this as negative 2x over 3 times x squared plus 1 to the positive 4/3. We made it positive by putting it, made the exponent positive by putting it in the denominator. Okay, and let's do one more where it looks a little bit confusing with that Leibniz notation. So we want to find dy dx, where y is in terms of u, and then u is in terms of x. Something that you could do, you could plug in x squared plus 1 into all of these u's right here, So it would be y equals x squared plus 1 to the 5th minus 2 times x squared plus 1 cubed plus 8, and just take the derivative of that. Technically, that would be correct, and you'd get the right answer, but let's do it the other way. So based on Leibniz notation, dy dx is going to equal dy du times du dx. So that means we take the derivative of this with respect to u, multiply by the derivative of that with respect to x. So the derivative of this with respect to u is going to be 5u to the 4th minus 6u squared, and that's it. Derivative of 8 is 0. Now we want the derivative of x squared plus 1 with respect to x. That's going to be 2x plus 0. And now we need to replace these u's with x squared plus 1. And we know to do that because the derivative says with respect to x, we want all of these with x's in them. So that's going to be 5 times x squared plus 1 to the 4th minus 6 times x squared plus 1 squared times 2x. And all I'm going to do here is just, I guess I can distribute the 2x. It doesn't matter too much. Let's distribute the 2x. We get 10x times x squared plus 1 to the 4th minus 12x times x squared plus 1 squared. And we can either leave it like that. I'm just going to factor out a GCF now. So you could have kept this 2x out, actually. Let's factor out a GCF of 2x times x squared plus 1 squared. Let's think about what's left over. From this first one, we're going to have a 5 times x squared plus 1 squared. And then from the second one, here, we're going to have a 6, and that's actually it. So we can simplify a little bit further. I'm just going to leave it like that. That's not the cleanest one in the world, so this is fine for our answer. Okay, so that is actually it for this section.